Chapter 11, Permutations, Combinations, and the Binomial Theorem. Let's get straight into it. Lesson 1. 11.1, Permutations, Part 1. Let's define this for now. We'll come back to it and further refine it. An ordered arrangement. So what's a permutation? An ordered arrangement or sequence of all or part of a set. Okay, intro. In how many ways can you walk from point A to point B in a 3x4 rectangular city? Pause this video, take a guess. Okay, this is a type of problem, a permutation problem that we will be able to solve later in the unit when we have some more skills. Okay, but pause and figure out how many possible ways. So you can go like this, provided that you get closer every step you make towards B. I can go like this. I can go like this. I can go like that. So there might be a lot. I don't know. Okay. Y is a 6-number password, so 1, 2, 3, 4, 5, 6, something like maybe 5, 3, 9, 1, 8. Better than a 3-number password like 3, 9, 6. Okay, intuitively, Y is this. Better than that. Okay, has something to do with permutations. Okay, let's investigate possible arrangements. You're packing clothes to go on a trip. You decide to take 3 different tops and 2 pairs of pants. If all the items match together, how many different outfits can you make? Okay, so if I say this is A, B, and C, the shirts, and this is pants P and Q, well, with each shirt I wear, I can pair it with 2 different pairs of pants. Okay, if you count all the outfits, I have 6 outfits. Or we can see that 3 shirts, 2 pants, 3 times 2 equals 6. Okay, part B. You also take 2 pairs of shoes. Shoe 1, shoe 2. State how many different outfits consisting of a top, a pair of pants, and a pair of shoes are possible. So shoe 1, shoe 2, shoe 1, shoe 2. Okay. Okay, how many possible outfits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So part B, 12 outfits. Well, how do we figure that? We counted it on the tree diagram, but also if I have 3 possible tops, 2 possible pants, and 2 possible pairs of shoes, well, that's 12 possible outfits. Determine the number of different outfits you can make if you have 4 pairs of pants, 3 shirts, 2 hats, if an outfit consists of pants, shirts, and a hat. So no more tree diagram. Let's think about this. 4 pairs of pants, 3 shirts, and 2 possible hats. Well, that's 4 times 3 times 2. That is 24 possible outfits. State a conjecture. Letter D. State a conjecture about how you can use multiplication only to arrive at the number of different outfits, parts possible, outfits possible in parts A to C. So number of pants times number of shirts times number of hats. Okay, that would equal total possible different outfits. A friend claims that he can make 1,000 different outfits using shirts, pants, and shoes only. So what if I have 10 possible shirts, 10 possible pants, 10 possible shoes? How do I do this? 10 times 10 times 10. I have 1,000 possible outfits. There you go. Next page. The fundamental counting principle. Consider a task made up of several stages. If the number of choices for the first stage is A, the number of choices for the second stage is B, choice for the third stage is C, etc., then the number of ways in which the task can be completed is A times B times C, etc. This is the fundamental counting principle. Example 1. Toys are fun manufacturing, producing multicolored wooden trains. Each train is made up of 3 cars. Car 1, red, blue, or yellow. Car 2, orange, purple, or green. Car 3, pink or brown. So car 1, 3 choices. Car 2, 3 possible choices for color. Car 3, 2 possible choices. How many different colored trains can be produced? 3 times 3 times 2, 18 different colored trains. Example 2, an electric box has 8 switches with the options on or off as its movement. Determine how many possible switch positions there are. So if I have a switch box, 8 different switches, let's just draw them out. Okay, on or off, so I have 2 different positions for each switch. Taking all 8 switches as a whole, right? What are the different possible switch positions through all? So I have 2 choices here, 2. Each of the 8 switches has 2 possible positions, and if I multiply them all together, right, shorthand, there's 8 2s, so that's 2 to the 8th. I have 256 possible switch positions. Example 3, James is allowed to have a 3-number locker combo for his new digital lock at the gym. He can have any number from 1 to 20 for all 3 numbers. Determine the number of possible locker combinations. So 3 numbers, folks, right? So it could be something like 14, 6, 11. Okay. How many different possible combinations are there? Well, let's use the fundamental counting principle. There's no restrictions, right? So let's just start with the first digit. Sorry, the first number. How many possible numbers from 1 to 20? Well, there are 20 choices. I can have repeat numbers in each part of the combination. So another 20 and another 20. So I have 8,000 possible locker combinations. Restrictions. When solving problems involving restrictions, it is important that the restriction is dealt with first. Very, very important. So example 4, let's show you an example with the restrictions. Ellie has been assigned the task of determining how many odd 3-digit numbers there are. She has been told that a number such as 875 is a 3-digit number, but very important, 083 is not a 3-digit number, it's a 2-digit number. So we have to account for cases like this through our restrictions. The first step of our work is shown below. Explain your reasoning for the number 5 at the end. So remember, we're doing fundamental counting principle. We're going to multiply 3 numbers together to find the number of possible cases. Okay? Why is it 5? Well, we want odd numbers, so the last digit of a number to be odd, right? So if I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 3, 5, 7, and 9 are your possible choices. So I have 5 choices. Oops, 5 choices. So that's why the number 5 is there. Okay. The second step of work is shown below. Why the number 9? Okay. Okay, we have 10 digits, right? But we've used one of the digits in this last place here, right? So start with 10 digits. We used one digit in last place, so 9 digits to choose from. Okay, last part, complete our work to determine how many 3-digit odd numbers there are. So 9 times blank times 5. Well, what goes here? Well, I'm going to put a note here. It says repeats of digits allowed. So the problem did not say repeats are not allowed, so I'm going to say they are allowed. So for this middle position, I have the digits 0 through 9. That's 10 different possible choices. Okay, so I put 10 there. So 9 times 10 times 5. Okay, so 10, sorry, let me finish this, 10 possible choices. So how many, let's complete this work. How many different 3-digit odd numbers are there? 9 times 10 times 5. That is 450 possible choices. Next page, explain how Ellie would need to adjust her work if the 3-digit odd number does not have any repeating digits, then determine the number of 3-digit odd numbers that have no repeating digits. Okay. Okay. Needs to be odd number, so we know this already. So odd number 1, 3, 5, 7, 9. This one, not 0. Okay. Not last digit. So not 0, not last digit. That takes out 2 of your options or 2 choices. So I'm going to put an 8 there, 8 possible choices. This middle one can't repeat first, last digit. So how many choices does that take out? It takes out 2 choices. So I have 8. Okay. Can't repeat first, last digit. Okay, but I'm going to note here, but can use 0 if it's not already used. Okay, so that brings it back to 8. So that's 8 times 8 times 5. And that gives you 320 possible 3-digit odd numbers with no repeating digits. Okay, help Ellie determine how many even 5-number digits there are. Okay, so let's try 5 slots. There you go. Even digit numbers. Okay, 0, 2, 4, 6, 8. I have 5 choices. Okay, this one 9 choices because not 0. And then this one, no restrictions, right? It says I can repeat, right? So repeats, okay. So I have 10 choices, 10 choices, 10 choices. Okay, and then that equals 45,000 possible even number 5-digit. So 45,000 possible even 5-digit numbers where the digits inside the number can repeat, and that's okay. Okay, part 2. How many even 5-digit numbers there are with no repeat digits? So let's draw our 5 slots again. Okay, no repeats. This one we're going to actually do in 2 cases here. We'll do the problem first, then I'll illustrate why this works. Okay, so case 1. When we have no repeats, this causes a problem with the way we count the number of possible cases, where if we don't do 2 cases, we're going to actually undercount. Okay? All right, so case number 1, 0 is last digit. So let's draw our 5 slots. Okay, only 0, so that's 1 choice. Next restriction, that first number, not 0, that gives us 9 choices. So if we've used the first choice, so last digit, first digit have been selected, how many do we have left for these middle 3? Okay, so 10 minus 2 digits already used, that's 8, 8, 7, and 6. So if we multiply everything, fundamental counting principle, so again, no repeats here. That's case 1 has 3,024 possible even 5-digit numbers that end in 0. Okay, last digit is 0. Or case 2. 0 is not last digit. 1, 2, 3, 4, 5. So that's 2, 4, 6, 8. So I have 4 choices. Okay, this one, not 0, not last. Okay, that's 8 choices. This one, only restriction, no repeats. So if I've used a digit, if I use the digit for the first and last places, then 10 minus 2, I have 8 left here, then 7, then 6 if I'm saying no repeats. Okay, 8 times 8 times 7 times 6 times 4, that's 10,752. Okay, total 3024. 0 is last digit plus 10,752. I get 13,776. Even 5-digit numbers, no repeat digits. Okay, on a separate page, I'm going to show you, so keep this number in mind. It's different than if we had done this with just one case. Okay, so let me just do another page here. Okay, so if I say just one case, okay, I want even 5-digit numbers. So there we go, even 5-digit numbers. If I just said this one is 0, 2, 4, 6, 8, okay, that's 5. And then this is not 0, not last. Okay, not 0, not last. So how many does that leave? 8 choices. And then this one, simply no repeats. Okay, so not first, not last, so I have 8 left here. No repeats, I have 7, then 6. What do we get? 8 times 8 times 7 times 6 times 5. 13,440. You're actually undercounting. Undercounts the number of even 5-digit numbers. From the previous example that we just did, 13,776 versus 13,776. So this one undercounts it. Okay, because if, let's do this, let's think about this. If for this first digit I have 5 choices, let's say I don't pick the 0, I pick one of these, then this 0 can go towards that digit, right? Because the 0 can be in the middle. Okay, that's one reason why we might be undercounting. Okay, if I choose a 0 here, then a 0 cannot be chosen for any of these middle digits. Again, so you can start to see some of the discrepancies, differences between counting this way and counting this way. So this one involves 2 cases. Just be careful, okay? Cases. This is important when you're doing these problems. Okay, next problem. Example 5. Determine how many odd numbers are less than 400. Show this using the fundamental counting principle. Okay, so let's break this up into cases here. 3-digit numbers. 1, 2, 3 slots. Okay, 1, 3, 5, 7, and 9. I have 5 choices. Okay, this first digit can only be a 1, 2, or a 3. Okay, because I need to be less than 400. So that first digit has to be a 1, 2, or 3. So it has to have only 3 choices. And then again, repeat digits are okay, so I can use any of the 10 digits. So in other words, like 355 is okay, 311 is okay, 313, all odd numbers. I'm using repeat digits, which is totally okay. All right? Okay. Case 2, two-digit numbers. 1, 2. I want odd numbers, so that last digit has to be 5. Okay, and then this one, any digit not 0. Okay, because I can't have 0, 5. So I have 9 choices. 9 times 5. Oops, this part. 3 times 10 times 5. Let me just multiply that. 150 possible choices. 9 times 5, 45 possible choices. Now, one-digit numbers. Okay, just one slot. 1, 3, 5, 7, 9. 5 possible choices. 150 plus 45 plus 5, that's 200 possible choices. Okay. Can we do this through like a brute force counting method? Sure. So if we think about this, 0 to 100, let's do groups of 100. So numbers like 0, 2, 4, dot, dot, dot. Oops, sorry. Odd numbers, folks. My bad. 1, 3, 5, dot, 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 all the way to 99. Well, we know odd numbers alternate with even numbers, so there are 50 numbers here. How about 101 to 200? So that's 101, 103, dot, 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 199. Well, 50 again. 201 to 300. That's 201, 203, dot, 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 all the way to 299. Another 50. Last one, 301 to 400. Odd numbers only, 301, 303, dot, 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 all the way to 399, 50. Well, all of that, still 200. Okay, so you can see the fundamental counting principle gives you a much quicker and easier way than just brute force counting.